acid-base properties of salt solutions. So salts, by that we mean ionic substances. These things are solid at room temperature. They've got cations and anions in a particular ratio. They're arranged in this crystal lattice structure, making them solid at room temperature, also known as ionic compounds. And when they do dissolve, they dissociate. These ions break apart from the crystal lattice and go into water. They become hydrated with water molecules. They become aqueous, and they go into the water. What we're going to be looking at is what happens if those ions don't just go into the water, but what if they start messing with the hydronium hydroxide ion concentration of that water solution? They would then change the pH of the solution itself. So if those ions change the equilibrium that water is sitting in, we know that water auto-ionizes, that they will, one water molecule will take the other water molecule's hydrogen ions, forming a hydronium and a hydroxide ion, and we know the K value for this is our Kw, which is equal to 1 times 10 to the negative 14 at 25 degrees Celsius anyways, and so highly favored to be on the left, but there is still some auto-ionization of water, and it is at equilibrium. If you add some ions that then disrupt this equilibrium, so they could do that by taking some hydrogen ions out of it, or they could be taking some hydrogen ions from the water and then increasing the hydroxide ions. So however they disrupt it, if they do, they end up changing the pH. They cause an imbalance in the hydrogen or hydronium and hydroxide ion concentration balance. So we will refer to this as hydrolyzing water. So you can imagine that if they start messing with water by either donating or taking hydrogen ions, then this will change the pH of the water. So if the salts ions hydrolyze water, then they affect the pH of the solution. And essentially what we're going to be doing is we're going to say, okay, here's our salt. We've got a cation, we've got an anion. We'll look at each in turn separately, and really what we're looking for is, are those ions going to act as an acid or a base in the solution? Do they hydrolyze water? And we'll do that by considering whom their conjugate partner would be and what we know about those conjugate partners. But really what we're just doing is we're saying, okay, are these ions going to act as an acid or a base? And if so, what's going to be the effect on the pH? We're going to do this mostly qualitatively, though we've already gone through how to do the quantitative calculations. As soon as you can nail down what the concentration is, then you can go back and do the actual calculations and figure out what the pH is if you knew what those concentrations of the different ions were. So how do you know if an ion will hydrolyze water? First, you want to look at what would be forming if the ion did hydrolyze water, and is it likely for that ion to be able to form that? So can the ion form that? What we'll do is we'll say, okay, is the thing that they're trying to form, so think of that as the conjugate partner of the ion, is that a strong acid or a strong base? And then if it is, the one thing we know about these strong conjugate partners is that they do not form, they unform. That's why they're strong. So if the ions are trying to form something that is a strong, if they're trying to form something that is a strong conjugate partner, then we know it won't happen. However, if the ions they could hydrolyze water and form something that is a weak conjugate partner, then again, what we know about weak conjugate partners is they're good at staying together, so they will form, and that will cause the hydrolyzation of water and the change in the pH. So it means that an ion will not shift the direction, so if it can't move towards these strong partners, if their thing that they could form is strong, then it's not going to form, and therefore we do not have the hydrolyzation of water. Let's go through this with some examples. So sodium chloride, common table salt, when you put that in water, we know it's going to dissociate into sodium and chloride ions. And so really what we want to do to figure out whether this will hydrolyze water is just look at each ion in turn. The sodium, so would sodium hydrolyze water? Essentially what it would have to do that would be say, okay, well, it's a positive ion, it's not going to take hydrogens away because it's already positive, but maybe perhaps it could pick up hydroxide. And this is what we're saying. So this sodium hydroxide, if it were to form, we're talking about a strong base here, and what we know about strong bases is they completely dissociate, so we know that's not going to happen. The chloride, is it going to hydrolyze water? If it was to do that, if it were to try to take a hydrogen from the water, then it would form hydrogen chloride, but the one thing we know about hydrogen chloride is it does not form. So the products that these ions would have to create by hydrolyzing water in both cases are strong, and therefore that tells us that that will not happen. These strong conjugate partners, they don't like to stay together. Therefore the reaction will stay on the chloride side, the waters will be safe, and we do not have any hydrolyzation of water. So this reaction stays shifted to the left. The ions don't act as an acid or base. They cannot hydrolyze the water. We know that by looking at whom they'd be trying to form if they did that. And they're forming things that are strong, which do not get formed. And therefore, the pH of a solution of sodium chloride will remain neutral. Potassium chloride. Let's look at this one. So potassium ions, again, it's not going to pick up the hydrogen, but maybe you can pick up some hydroxide or something. But we know potassium hydroxide, that's not something that's going to form. That's something that it will unform. It dissociates. So we know that's not going to happen. But the chloride ion, could it take a hydrogen from water? So the question is, if the chloride ion did take a hydrogen from water, it would be forming HClO4, perchloric acid. And what we know about perchloric acid is that that is a strong acid. And because it's a strong acid, that means it doesn't form. Strong acids like to not form. They like to be unformed. They like to completely dissociate. And so in both these cases here, the two ions will not shift to the right. They will not mess with water. They're not going to hydrolyze water in any way. And therefore, we have the pH of a potassium chlorate solution will also be neutral. Now, how about ammonium chloride? So we've got an ammonium and we've got a chloride ion. Let's look at the chloride first because we've already done that. So we know the chloride would be trying to form a strong partner. So we know that's not going to happen. So chloride does nothing to the water. But the ammonia in this case here, could it hydrolyze the water? And in this case, again, it's positive. So we're not going to be taking a hydrogen from water. But what it could do is it could donate a hydrogen to water and form ammonia. Now, we need to decide, would that happen? And we know it will, because ammonia is a weak conjugate partner. And what weak conjugate partners do is they exist. They stay together. That's what makes them a weak base in this case. And so we know that this system here will actually exist at equilibrium. So we know that there's going to be some changes taking place here. We know that the ammonium is going to donate some hydrogen, is going to be donating some hydrogens to the water and forming the ammonia. And as you can see, when that happens, it messes with the equilibrium that water is sitting at. We're creating some hydroniums, and of course that's going to have an effect on the pH. So because the cation here can act as an acid, it is going to hydrolyze water. It's going to act as an acid. The anion's not doing anything in this case, so we can just not worry about that. We know though that this ammonium is going to be acidifying the water by creating these hydronium ions. If you wanted to consider, because again, I don't think of any way that this could happen, would the ammonium take the hydroxide ions out of the water maybe by forming NH4OH, the ammonium hydroxide? But these particles don't really exist. One thing we know that is that, like, if you do form them in a double displacement reaction, they immediately break down. So essentially, we don't need to worry about that. If you really did want to worry about it, you'd be like, okay, let's pretend it did happen. So we would pick up hydroxides and we'd form this ammonium hydroxide. But we know from our double displacement reactions that ammonium hydroxide immediately breaks down to ammonia and water. And so then we could say, okay, well, maybe then the ammonia and the water react and it takes some hydrogens from water. Wouldn't that count as hydrolyzing water? And then that would give us some NH4 and more importantly, the OHs. But take a look at this entire reaction. We'd say, okay, well, if we are saying that these three things happen, then really what we're saying is nothing's happening, because all of the reactants cross off all of the products. So even if you do want to say it happens, there is no net change. So in other words, don't say it happened. Just look at the ammonium donating hydrogen, not picking up hydroxides. How about sodium acetate? So throw this stuff into water. It's again ionic substance. If you throw it into water, we already know the sodium ion is not going to be able to form sodium hydroxide because that's strong. And then if we look at the acetate ion though, would it be able to pick up a hydrogen from water? And so we know the sodium does nothing. We do know that if the acetate ion picked up hydrogen from water, it would form a weak conjugate partner. Therefore, it will happen. This will exist in an equilibrium situation. There'll be some acetate ions, there'll be some acetic acid, and because that is going to happen, you also form some hydroxide. So essentially, the acetate ion is going to act to increase the concentration of hydroxide ions, making the solution basic. So if both ions can hydrolyze water, the pH will be determined by who's better at doing it. So we saw some examples where sometimes the cation can do it, like with ammonium, and sometimes the anion can do it, with acetate we saw that happening. So what happens if they both can do it? Then it's just going to be a matter of comparing who's better at hydrolyzing water. If the Ka of the acid is greater than the Kb of the base, then the acid's better at being an acid than the base is at being a base. Therefore, the solution will be acidic. If the base is better than the acid, it'll be basic. And if they happen to work out to be exactly equal, then the solution will still be neutral, even though there is hydrolyzation happening. Ammonium acetate. Here's our example here that we've seen the two pieces come together already. But we do know that the ammonium will form ammonia. So this system will be at equilibrium. The acetate, its conjugate partner is weak, and therefore this system is going to be at equilibrium. Therefore, we're going to be producing hydronium ions and hydroxide ions. The question is who is better at doing it. So both of these are going to hydrolyze water. To know who's going to win, you compare the Ka of the acid, so how good is the ammonia at shifting to the right versus how good is the acid at shifting to the right. Now you need to look at the Kb of the acetic acid, not the Ka of its conjugate partner, but the Kb of the acetic acid, because it's the one that's actually doing the job. So its ability to be a base is sort of represented by this Kb value. The ability of the acid to be an acid is sort of represented by this Ka value. And again, depending on where you're pulling your data table from, you may be able to get a more precise or slightly different number. But if they did happen to be the same value, then we would say that the solution is neutral. If one is bigger than the other, then we know it's going to be the winning one. And again, depending where you get your Ka or Kb values, they may not be exactly as these ones are. So work with the numbers that you have. Now we know some ions can be both acids and bases. So what happens if you have one of those ions in there? Same idea as before, is that if it can be an acid and a base, now this time it is the single ion that is trying to be both an acid and a base. So you have to look at its Ka versus its Kb value. Is it a better acid or is it a better base? Things that are amphoteric. So for example, sodium bicarbonate. The sodium we know is not going to do anything, but the bicarbonate could hydrolyze water, and in this case here it is picking up a hydrogen from water, so it is acting as a base and producing hydroxides. But because we do know that will happen because we have a weak acid here being formed, so we know that this system will exist at equilibrium. And because it's amphoteric, we could say, okay, well, maybe it's going to interact with water and it'll donate its hydrogen to water, forming the hydronium. And again, we look at the partners here. They are both weak, so we know that this system is going to be at equilibrium. So this will happen to an extent. The question is, which one will happen more? And it will be the winning one to determine whether the hydrogen carbonate is going to be an acid or a base. So you got to be careful. You got to look at the hydrogen carbonates, its Ka value of it acting like an acid. In this case here, you're saying, okay, is it going to act like an acid, or its Kb value in that case here? And remember, bicarbonate and bicarbonate, these are not conjugate partners. They're the same thing. So you can't just find the Ka value for bicarbonate and then do the Kw equals Ka times Kb to find the Kb value for hydrogen bicarbonate. Sorry, hydrogen carbonate. Because that Kw equals Ka times Kb, that is for conjugate partners. So the Ka and the Kb, they have to be the conjugate partners of each other. Bicarbonate and bicarbonate are not conjugate partners. It's the same thing. So you have to use one of their conjugate partners to find the Ka and the Kb of the hydrogen carbonate, bicarbonate. Just make sure you're getting the right Ka and the right Kb values. So this one here, we have a Ka value. You could probably find it for the bicarbonate. I don't have them listed here. There we are. There's the Ka value for the bicarbonate and the Kb value for the bicarbonate. And again, remember, these are not conjugate partners. These are both bicarbonates. So make sure you get the right Ka value. You want the Ka value for bicarbonate and the Kb value for bicarbonate, not something like the Ka value for H2CO3. You could use that to find the Kb value for HCO3, but just make sure that when you're using the Kw equals Ka times Kb, that is only for when you're talking about conjugate partners. In this case here, you have to find it for bicarbonate and for bicarbonate as in this case, acid, and in this case, a base, the Ka and the Kb values. Should be approximately these numbers here. Now, obviously, the Kb value is many times bigger than the Ka value, which means Bicarbonate is a much bigger base, making the solution basic. Now, when it comes to actually then quantifying what this pH will be, it's just a matter of figuring out what the concentrations of those ions are. So once you're aware of which ions can hydrolyze water, figure out what their concentrations are, and then just treat it as it is a weak acid solution or a weak base solution, depending on how it's going to hydrolyze water. But find its concentration, use the Ka value, and then solve for pH. You can go back and look at a video on doing calculation for weak acid solutions to find out how to do those particular calculations.